All right, welcome to number 3. We're going to calculate the energy transfer in a wall section measuring 2 by 1 meters and 0.04 meters thick with a thermal conductivity of 0.1 joules seconds meters Celsius. What that means is that's how fast thermal conductivity, how fast the energy can flow through a substance like the wall here. Opposing sides of the wall have a temperature of 10 and 5 degrees Celsius after 1 hour. As before, let's write down what we know. So our initial, our values, and our final. Well, we know our initial temperature, Ti, is 10 degrees Celsius. We know our final temperature, Tf, is 5 degrees Celsius. We know what the area is, 2 meters by 1 meter. So you multiply those, you get 2 meters. We know our constant, 0.10. That's joules second meter Celsius. We know the thickness of the material, represented by L, 0.4 meters. And we know the change in time. That's 1 hour. And that's equal to 3,600 seconds. And we also know that there's a change in temperature. All right, that's 10 degrees Celsius minus 5 degrees Celsius, which is going to give us a total difference of 5 degrees Celsius. Those lines a little longer. I think that's about all we know. So, some things to solve for. They're asking what is the rate of temperature change, and that deals with time, like how fast does the energy transfer through the wall in 1 hour. So, let's put that down here. That's going to be represented by P. P is the rate of heat transfer, and they also want to know how much thermal energy, so that's represented by Q. Let's look at our documents here. We're going to be using this formula. We have our area, our constant, time, thickness, and then up here we have what P is equal to, energy transfer over time. So we're going to be using those two formulas. So let's write those down. P is equal to, let's move that up so you can see it, the thermal energy by the change of time, and then P is also equal to how thick the material is, or sorry, the constant, the thermal conductivity right there, thermal conductivity times the area, and then times the change in temperature, and put all that over however thick the material is. Obviously, the thicker the material, the longer it's going to take. Okay. Let's solve for Q, so we're going to change this around. So we'll move the Q over here, and that's going to be the P times the change in time. All right, and then let's substitute P. So put in the P formula right there. He said P. So Q is going to be equal to the K times the area times the change in temperature. Put all that over L. All right, and that's going to get multiplied by the change in temperature, time. All right, change in time. So this is the formula that we're going to be working with right here. We got that by combining those other two formulas. So let's do some substituting and solving. All right, so Q is going to equal 0.10 joules, seconds, meters, Celsius, times the area, which is 2 meters cubed, times the temperature difference, which is 5 degrees Celsius. All of that gets put over the thickness of the material, 0.4 meters. This whole shebang is going to get multiplied by 3,600 seconds. Okay. Let's do some crossing out. Okay, right away, we can cross out one of the meters here and the other meter there. We can cross out Celsius right there and there. And we can even cross out seconds because we got seconds over here and seconds over there. Okay, let's multiply this out. We're going to be left with, that's going to be 1. I know, nice easy number, over 0.04. All right, that's actually got to bring down the joules. And that's going to get multiplied by 3,600. All right, multiply this out, or divide this out, sorry. You're going to get 25 times the 3,600, and we end up with 90,000, there's a J in there, joules. And that's going to be equal to our Q. So that's how much energy is going to pass through that wall in 1 hour. All right, welcome number 4. Determine the R value of the wall cavity. In order to get this, you're going to be using this chart. Okay, so you can look at like fiberglass battens right here, and you come down here and you find fiberglass batten is 3.142 R value per inch. And if you look, this is 6 inches long. So you're going to have to multiply that 3.142 times 6. All right, so I'm just going to give you the numbers. We're going to do the wall cavity first. All right, the wall cavity is this pink area, like right here, because this area is different than down here where there's a piece of wood. So we're going to figure this out first. All right, first thing we have is drywall. All right, if you look at your chart, drywall is 0.56 for 5/8 inch drywall. Fiberglass, we just talked about, and that's going to be 3.142 times 6 inches. And that's going to give you an R value of 18.9, so we're just going to round it up to 19. Okay? And then our foil face styrofoam, real fancy stuff. It's got a nice high R value of 7.2. And this stuff works really well, 7.2. I'll zoom in a little bit there. Let's move on. Air. Well, they give you the air. Right there, airspace is 0.17. Okay, and then we got some brick. Now the brick, okay, they give you some measurements here. So let's look down here. So we got a brick drawn out. Okay, it's going to be 8 inches that way, and it's 3.5 going this way. This is the direction that the energy is going to go through to get through the brick. All right, so that's how you figure that out. So we're just going to use a brick that's 4 inches. So we're going to use a brick that's 4 inches, and that's going to be 0.8. Okay, all you got to do, add those together, and that's going to give you your R value. So add all those numbers together. Now, not only do we have a wall cavity, we also have where the wood stud is located. Okay, so we're going to use the same things. Again, we have drywall. We're down here now, so we're going through this area. So we have drywall, that's 0.56. We have the 2x6 wood. If you know that, if you look at it, wood is 0.94 per inch, and we have 6 inches, so that's going to give us 5.64 for an R value. Okay, so that's going to be our R value for the wood. And then we have the foil face again. That's going to be 7.2. We have our airspace. That's going to be that. And then we got our brick again. So a lot of these numbers are going to be exactly the same, 0.80. Once again, R values, you just add all of them together. So add those together to get your final answer. And you will get an R value of 14.37. And then for the wall cavity itself, you're going to get an R value of 27.73. So what that means is, up here where you don't have wood, it's going to be a better insulator than down here where you have the piece of wood. All right, this is usually the bottom of a wall, so it's very small. Okay, so that's how you get the R value of materials and its ability to resist the flow of heat.